Ever wonder how scientists identify a mystery molecule? They don't look at it, they weigh it.
Welcome to mass spectrometry, or MS, the most powerful scale in the world of chemistry. Instead of light, MS uses high-energy electrons to smash molecules into charged fragments. These fragments are separated by weight and charge, creating a unique fingerprint for every substance. From drug testing to space exploration, if it's matter, MS can identify it. Let's dive in.
Mass spec isn't new. It actually dates back to 1898, but the real breakthrough happened in 1911.
Physicist J.J. Thomson used a primitive mass spectrum to study the element neon.
Expected one signal, but he found two, neon 20 and neon 22.
This proved that atoms of the same element can have different weights. We call these isotopes.
Today, MS is so precise it can tell these apart instantly. Next, let's see how the machine actually works.
Every mass spectrometer, no matter how expensive, does exactly three things. Think of it like a car wash for molecules.
Ionization. We blast the sample with electrons to give the molecules a charge. They're ready to move. Second, separation. We use magnetic or electric fields to sort the ions based on their mass-to-charge ratio. Finally, detection. A sensor counts how many ions of each mass hit it, creating the data we see on screen. Ionize, separate, detect. That's the magic formula. Up next, we look at the ray gun, the ion source. IR, NMR, UV. Most spectroscopy uses light or energy waves to tickle a molecule. But mass spec is different. It doesn't use the electromagnetic spectrum at all. Instead, we use a beam of high-speed electrons. We aren't just looking at the molecule, we're breaking it. This makes MS a destructive technique. Once your sample goes in, you aren't getting it back. But the reward is worth it. The exact molecular weight.
Before we can weigh a molecule, we have to get it inside the high vacuum environment of the spectrometer. We use a reservoir inlet. It uses a molecular leak to let in a tiny, steady stream. For solids, we use a direct insertion probe. We place the sample right into the ionization chamber. The key is maintaining a vacuum. If air gets in, the high-energy electrons will hit oxygen instead of your sample. Once inside, it's time for the fireworks. Next up, electron impact ionization, the molecular smash. Inside the ionization chamber, we use the electron impact method. Think of it as a high-speed collision.
A heated filament shoots out a beam of electrons at 70 electron volts of energy. That is a lot of punch.
When an electron hits your molecule, it doesn't stick. It knocks another electron off, like a cue ball hitting a rack.
This leaves us with a radical cation. It's now positively charged and ready for the magnetic field.
But beware, 70 eV is so strong it often shatters the molecule into pieces.
If a molecule survives the electron blast without breaking, we call it the molecular ion, or M+. Since it only lost one tiny electron, its mass is essentially the same as your original molecule. On your spectrum, this is usually the peak at highest MZ. It tells you the exact molecular weight. Wait, some molecules are fragile. If the M+ peak is tiny or missing, it means the ion shattered instantly. Stable rings show big M+ peaks. Branched chains don't. Next, let's see the peak that wins the popularity contest.
When you look at a mass spectrum, one peak always stands taller than the rest. Meet the base peak.
We give this peak a relative abundance of 100%. It's the gold standard we use to measure everything else.
Why is it the tallest? Because it represents the most stable fragment formed during ionization. Graphic. Two peaks side by side. One is at 100, the other at 50, with percentage flashing. Instead of a direct hit, we use a reagent gas like methane. We ionize the gas first to create a plasma.
Wait, some molecules are fragile. If the M+ peak is tiny or missing, it means the ion shattered instantly.
Instead of a direct hit, we use a reagent gas like methane. We ionize the gas first to create a plasma.
Ionized gas bumps into your sample, gently transferring a proton. It's a soft nudge rather than a punch.
What if your molecule is too big and heavy to turn into a gas, like a protein or a strand of DNA?
Standard methods would just burn it. Instead, we use MALDI. We bury the sample in a special matrix.
Or we use electrospray. which sprays the liquid through a high-voltage needle to create a fine mist.
These soft tricks let us weigh the building blocks of life. Next, let's see how the ions actually move. Now that our molecules are charged ions, they're just sitting there. We need to get them moving, fast.
We use two metal plates with a high voltage between them. Think of it like a giant electric slingshot. Since our ions are positive, they are repelled by the positive plate and pulled toward the negative one.
They fly through a tiny slit in the plates, forming a narrow beam of ions heading for the analyzer. They are now racing at incredible speeds. But how do we sort them? Next up, the magnetic curve.
Now the ions are racing. To sort them, we make them fly through a powerful magnetic field. Think of it like a car taking a sharp turn. The heavier the car, the harder it is to turn.
Light ions curve easily. Heavy ions have more momentum and resist the curve.
By changing the magnet strength, we pick which MZ, or mass-to-charge ratio, hits the exit. It's a perfect filter. But what if we don't want a magnet? Next, the four-pole filter.